Okay, awesome. Thanks so much for joining, and thanks to the organizers, Kushani and other organizers for inviting me to talk. I'm very happy to talk again at the ICC MM on this special session in dynamical systems and applications to, all kinds of scientific applications. So my topic today is the long-time dynamics of a model for Alzheimer's disease. This is a little bit out of my wheelhouse. Usually I work in more sort of ecological applications, but in this particular work, I decided to foray a little bit outside my wheelhouse. And this is joint work with a group in India, Ranjit Upadhyay, who is at the IIT Dhanbad, and Paramita Roy, who's at the Thapar Institute. And the student on the paper is Debashish Pradhan, who's a Upadhyay student. Brief outline of the talk is I'll give you a little bit of the biomedical background. I won't say too much here in an hour-long talk. Maybe I could go into more details. Uh, but in a 30-minute talk, I'll probably jump straight to the modeling. The work is in two parts. Basically, the ODE case and the PDE case of the model considered. My work in this particular paper was in the PDE case, so I'll really talk about that. So it's a little more PDE heavy, but I will try to give you uh, the big picture. I won't really talk about the ODE case except just for motivation. And the PD case will lead to the main dynamical feature that we consider here, which is a proof of the global attractor for the system considered. And then I'll end with some interesting at least to me, future work, which I think is will possibly be interesting to people in the audience as well who work in noble language dynamics. So there are some connections. All the connections are not clear, but that's why it is in the space of future work. So that's the rough outline. Okay, so let's get started. So the definition of AD. So AD is the most common type of dementia, which is a loss of cognitive function. It is progressive, so starts perhaps with mild memory loss and can lead to serious neurodegeneration. So it is a serious mental health issue. It is the sixth highest cause of mortality in the US, with AD-related deaths doubling in about the last 20 years. Many factors contribute to AD: aging, obesity, diabetes, all appear to increase a person's vulnerability to AD. But these other factors of how diabetes links to AD has not been looked at too much from the mathematical modeling angle, at least to the best of our knowledge. So several control methods for AD have been proposed, but a person with AD rarely improves completely. So this project of Upadhyay and gang basically looks to couple rigorously diabetes and obesity functions with AD, with a view to control or delay AD by then controlling the diabetes or the obesity. So there is clearly a link using some differential equation techniques. You can link the two, and then one can look at control of AD by looking at control of the variables in the diabetes obesity class. That is the goal. Okay, so there are these two separate routes. One is the standard obesity and diabetes route, right? You got glucose intake, and if things are out of whack, then the insulin resistance increases, which causes an increase in blood glucose and damages the beta cells. There is a link to this and the microglia, which can cause inflammation inflammatory producing cytokines, which can all then break through the blood-brain barrier, right? So the link is at this chain here, where they link this sort of increased, insulin production to the microglia formation, the production of cytokinase, which then causes these, AB plaques breaking through the blood-brain barrier and then causing serious neurodegeneration and cognitive decline. All right, so how what I just said is, essentially seen in this plot here. So, right, essentially diabetes has to do with the fact that, glucose can't be modulated uh, properly, and that causes problems in the insulin production and beta cells, which can lead to this production of cytokinase, which leads to activation of microglia, causing these AB tau plaques forming, breaking through the blood-brain barrier, and then causing neurodegeneration, which is the main cause of AD. All right. So, what is the mathematical model, or how can break this into a big mathematical model? So you see, there's a lot of levels. There's the glucose, insulin, beta cell going on. That's one level. These are feeding into the cytokinase, microglia, AB, and tau plaque formation. That's like, another set of things going on. Finally, these are sort of breaking through the blood-brain barrier, causing neurodegeneration, and that's leading to the cognitive decline. So that's like the third piece. So all these three different pieces have to be connected by mathematical modeling. Okay. All right. So let's look at some models. That is just some formation of beta and tau plaques that would, cause delay of signals, for example, in the neurotransmitters, causing the various neurodegenerations, loss of memory, cognitive function, and things. Okay, so here is the basic mathematical model, and this is the only time that I'll talk about things in the ODE sense. So you can think of this large coupled system in three parts. Let's look at G, I, and B. G is the glucose. So this is the rate of change of glucose. I is insulin. B is the beta cells. And then you have the beta cells, the tau plaques, the microglia. This is, C, M, and AB, those variables. And finally, those affect neurodegeneration. N and CD are the neurodegeneration and cognitive decline variables. And what you can see is clearly, if you have these tau plaques, XT, then they're acting as a source term. So the more tau plaques you have, the more is neurodegeneration, right? And the higher that is, the worse it is for the patient. And cognitive decline is directly proportional again to the neurodegeneration. The more neurodegeneration you have, the higher is cognitive decline. In the GIB, you have glucose, which has, some kind of logistic control, but is modulated by insulin. Insulin decreases, but is also modulated by the beta cells, and then the beta cell couples back to the glucose. So for the purposes of this talk, I'll focus on a smaller subsystem. Instead of looking at all of these 9 equations, I'll look at analyzing the GIB equations, and I'll tell you what the big problems are in the whole system, and then how we get around that. So this is the basic ODE setup, ODE models of the state variables. But of course, if you want to consider diffusion, a lot of stuff is diffusing in the brain. So you want to consider a reaction diffusion equation system, and that is given by system 2. So glucose is diffusing. So this is the diffusion is just modeled with standard Laplacian. Insulin is diffusing. But if there's beta cells, there's no diffusion in the beta cells. The logic here is that the beta cells go to steady equilibrium much faster than the glucose and the insulin. So there is no diffusion assumed in the beta cell. Likewise, there's diffusion in the microglia, AB, beta plaques, tau plaques. That is all these terms. But neurodegeneration and cognitive decline are state variables that are measuring uh, neurodegeneration and cognitive decline. So you really can't really think of diffusion there. Nothing really is diffusing there, right? Your state, your neurodegenerative state can sort of, decay over time as an AD patient, and your cognitive decline can also increase. But what exactly do we mean by diffusion of those variables? So there really is no diffusion. So if you look at two, it's a complicated system, but what complicates things more is there's diffusion only in some variables, namely 6 out of the 9 equations, but in a lot of them there isn't. That's the ones I've put in blue. All right. So that is an example of what is called a partially dissipative or partly dissipative system. And the analysis of that is quite difficult. Uh, so I'll focus on how we sort of got around that today. So the first result is very classical. Everything's bounded here. If you give me data in L infinity, all solutions will remain in L infinity, and you can do like an invariant region proof. So I won't read out the whole result, but essentially it says that if you give me bounded data, solutions are bounded. And classical, techniques work there. Say if you are interested in these things, you can look at uh, the book by Henry, for example. Okay, now what are we interested in? We are interested in the long time dynamics of this reaction diffusion system. So there are some dynamical system concepts that we have to understand before we analyze the long time dynamics. There's lots of good books on this. I'm following You and Cell. There's many others, Timom's book, Robinson's book. But all of this boils down to proving that things get absorbed in a certain function space. Okay, so some definitions before we get into technicalities. So bounded absorbing set, bounded set script B in a reflexive Banach space H is called a bounded absorbing set if for each bounded subset U of H, there is a time T, which depends on the initial data, such that the semi-group of solutions acting on this initial data will get inside B for T greater than this capital T. So if you wait long enough, you'll enter this absorbing set. And this time T is referred to as the compactification time, the time after which the semi-group forces the solution to enter this set. Okay, next, global attractor. So what we are after is trying to prove a global attractor for this reaction diffusion Alzheimer's system. So what is the technical definition? A non-empty subset A of H of the phase space is called a global or maximal attractor if three things are essential, three signatures hold, all right? A is closed and bounded. A is a closed and bounded subset of the phase space. A is invariant, so that if you're on the attractor, you'll always stay on the attractor. So that is given by, right, this definition here. S of T acting on A will be inside A. And A attracts every bounded subset B of H. So the limit of the difference, if you pick up any set B of initial conditions anywhere in the phase space and let solutions evolve from there, the distance between that to H will go to 0 eventually. Okay, so we want to show the existence of a global attractor for 2 being that Alzheimer's system in 1 and 2D. So the brain really is a 3D object. However, for some technical reasons, we don't have 3D yet. So one is really a toy model. It's not relevant here. 2D you can think of as a slice of the brain. So if you slice through the brain and look at a 2D slice, then that is where we are living our physical space. And the phase space is L2, so 9 copies of that. And X is a little better space. That's H1. That is essentially space of the function and its derivatives are in L2, and there's 9 copies of that as well. All right, so we want to show that there's a global attractor for 2. So let me give you some intuition for what is a global attractor before we get to the global attractor in the PD case. In the PD case, it's a little bit technical, but in the ODE case, it's fairly easy to understand. All right, so the global attractor from these three in layman's terms is just what all the dynamics go and sit on after a very long time. So it's like steady state is clearly a global attractor. So if you think of the ODE u dot equal negative u and take positive initial data, everything after a long time will go and hit the zero state. So zero is the global attractor. You wait long enough, right? You will be very close to zero. Now, if you change the ODE and you think a u dot is equal u into 1 minus u, that's the logistic ODE, then 0 and 1 are both steady states. 1 is stable, 0 is unstable. The global attractor is both those states and everything in between, all connecting orbits. So in that case, the global attractor is 0 to 1, the interval 0 to 1. So those are some simple intuitions for what, the global attractor is for some simple dynamical systems. Things can be much trickier in the ODE case as well, right? For example, people might have seen the Lorentz attractor, the Lorentz system. I don't have the ODE system here, but it's a system of three, nonlinear ODE. Lorenz was trying to model some, fluid mechanical behavior, and he reduced his PDEs by truncating to 3 sets of ODEs, and you run them long enough, and they seem to settle down into something that looks butterfly shaped in, 3 space. Uh, and they seem to match all those definitions of attractor, but there's no way to predict where the trajectories is going. All right, you take any 2 trajectories, they'll be close, then they'll go far, they'll come close again, they'll always sit on the attractor. Uh, but they seem to be, random in nature, although everything is coming from a deterministic system. So so-called, aka chaotic attractors, uh, classified by, non-integer dimension and things like that. So even for simple ODE, well, maybe not so simple, but once say you have 3 ODEs or more, you can have very complicated dynamics. They don't just have to be steady state or intervals or limit cycles. It can be much more complicated than that. All right. Now, in the PDE case, how do you prove a global attractor? In the ODE case, you basically try to prove, something is bounded and things will go and stay there essentially, right? Because in Rn, compactness and closed and bounded is one and the same thing. All right. But in the PDE case, in infinite dimensional phase spaces or function spaces like L2, bounded is not compact, right? So you can take, say, an L2 ball is bounded in L2, but not compact. Okay, so what do you have to do? How do you prove something is, say, an L2 attractor? Well, you have to show some kind of compactness in L2. But boundedness is not good enough because bounded is not compact. So you have to prove compactness using some kind of embedding theorems. That's the idea. So that's why initially I define this X space as well, H1. This one actually embeds compactly into L2. So if you're chasing a global attractor in L2, you will actually have to make some much better estimates than L2, maybe in H1 and then embed. So that's the big idea. Okay, so you'll have to show compactness, you'll have to show invariance, and then you will have to show some kinds of bounds. Uh, and the the boundedness is not so difficult. What is more difficult is the compactness. So we use some asymptotic compactness properties. So let's just define that. You say a semigroup is said to be asymptotically compact in L2 if for any bounded sequence in L2 and a sequence of time, you actually have a convergent subsequence in L2. Now, a bound in L2 will never give you a strongly convergent subsequence. That's the basic functional analysis. All right, you'll only get weak convergence. You need a bound in much better than L2, say in H1. So you have to work a little harder. So that's why we introduce X, and we will actually try to bound things in X. Now, the L2 estimates are pretty straightforward. I won't spend too much time. You basically do these things, by testing the equations against various functions. So you take the G equation, multiply by G, integrate by parts, use some inequalities, Holder-Young, Grunwald type inequalities to basically get a bound like 6. That is, if you give me any initial data, I can give you a time which depends on that initial data, such that as long as you wait for that much time t1, then the L2 norm of G will be inside this fixed ball of this fixed radius. This radius only depends on the parameters in the problem, not on initial data in any way. It doesn't matter how big the initial data is. So this is fairly easy. So you can do this for all the state variables and get L2 bounds on all of them. So the bounded absorbing set in L2 is quite trivial. Okay, I won't spend too much time on that. Uh, so how do we make the H1 estimates and what are the difficulties there? So let's see. If you want to make H1 estimates for G and I, you've got the Laplacian, you've got the smoothing. So once you multiply by G, you will have a gradient term. If you multiply by Laplacian, you'll have a Laplacian term. So all that is very easy for G and I equation. But the B equation doesn't have any smoothing. Okay, so how do you make a gradient estimate in B? So how do you deal with that? So the theory for such systems where you don't have full dissipation was actually initiated by a student of Temam, Martin Marion, uh, quite some time back. And you can uh, see a beautiful exposition of the theory in Temam's 2012 book, but the first papers appear in the late 80s and 90s. This is one of them, one of the Siam papers where they appear. The basic technique, without going into too much detail, is that if you want to show compactness for these kind of partially dissipative systems, what you have to do is split your solution into two parts, let's say an S1 and an S2, where S1 has the regularity that you want, S2 does not. It doesn't perhaps have the dissipation like that B equation. But you can prove a decay. You can prove a decay result. So because you can prove a decay result on S2 overall, taking this decay into the incorporation using Marion's theories, you can actually prove regularity of S, even though S2 is not regular. So that's the big technique. So we are not reinventing the wheel. This technology is fairly well known. Uh, so you can make H1 estimates in G very easily. It's standard. You multiply, by G first, and you have an integral in time of the gradient. So using mean value, you'll have some intermediate time where you can get an estimate of the L2 norm of the gradient of G, such as 13. And then you multiply by Laplace, that's the second estimate, uh, and use a sort of bootstrapping argument. All right, so it is not so difficult. Uh, I'll just give the final estimate. This is 18. You have see a uniform in time estimate for the gradient of G, as long as you wait long enough. The right hand side depends only on problem parameters, not on initial data in any way. Okay, now how do you deal with the B component? What do you do? So here we have to use some tricks. Uh, the key result here is that uh, you can find a super solution for B, say B star, where the gradient of the super solution, where the gradient of B is bounded by the gradient of the super solution. There is some work that goes into showing this, but you can derive that. Now, what do you do to the B equation after that? In light of Temang's and Marion's methods, you split B into two parts, B1 and B2. And the way I'll feed the initial data is that I'll give all of the initial data to B1 and say no initial data to B2. Okay, then I will write the B1 equation as negative C2B1 and the B2 equation to incorporate the other two terms. Now B1 has no regularity, but proving decay here is very easy, just by ODE comparison. Okay, and on B2, you can make the regularity estimates that you want by brute force, taking the gradient of the right-hand side where you have gradient of G, right? But the trick is that, right, the gradient of G, we already have the estimate. So that is injected in later. So by that, you can make some uniform gradient estimates in B2. So then you look at a Grunwald type inequality for the whole thing, where you've got a decay term of the gradient plus this extra integral term. But since the way we fed the data is zero, so we don't have to deal with this. So essentially, we can manipulate Marion's technique to show regularity for the B equation, although the B equation doesn't have any diffusion. So that's how you deal with these kind of systems which don't have smoothing. Now, if you understand this technique for these three equations and what I did, it essentially follows for the bigger system. There's no difference. If you go from C to tau, everything has diffusion. There's no problem. And then you play the same game with the neurodegeneration and the CD. So you can prove the gradient estimates for all of them, for all the state variables. All right, so let's see. Let's go there. Okay, so once you have the gradient estimates, then you use compactness of H1 into L2 to prove the asymptotic compactness part. That is the strong convergence in L2. And then you can prove similar results for at least this subsystem. All right, that is, say, the first three equations. So the reaction diffusion 9 possesses a H1 global attractor. H1 here is right, not the function space L1, it is L2, right? We only work in L2. And then you extend this to the full system by doing exactly what I did. The same trick will work without too much trouble. All right, so that way we can finally state the main result. If you consider the reaction diffusion system described via 2, that is the full AD system, the weakly dissipative system, There exists an HH, so an L2 global attractor for the system in space dimension n less than or equal to 2, which is compact and invariant in H and attracts all bounded subsets of H in the H metric. So the slice of the brain will work. We are not able to do 3D yet. That's because there are some issues with embedding here. Without getting too technical, in 1 and 2, you can make essentially get an L infinity estimate. But from H1, with some more work, actually, you can only do it in n equal 1. In n equal 2, it's LP for NEP, and with some more tricks, you can get L infinity. But in 3, you can only best do L6. So we can't quite take supremum bound. So 3 is little out of reach right now, but maybe sometime in the future. Uh, so we'll have to think more about that. Okay. The proof is textbook. Essentially, as I explained, it's just making sure you have those steps. You have well-posedness with theorem 1, so that you have a well-defined semigroup. You have the existence of a bounded absorbing set in H, that is the L2 estimates. That's easy. Then you use this Marion and Temang's technique to get the gradient estimates, even though there's lack of smoothing. So you actually have an X estimate, an H1 estimate. And then you use the Sobolev embedding of X into H to get the strong convergence in H, or the asymptotic compactness in H, or L2. So you have the L2 L2 global attractor. Okay, I'm a little out of time. Give me maybe 2, 3 more minutes. I will conclude with some future directions, which are interesting. Uh, so I want to get into and talk about how language dynamics and what thoughts we have for language dynamics going forward. So languages, right? I mean, this is a whole separate research topic, but they compete, right, like species, like biological species, for speakers in a population. This is the famous Strogatz and Abrams Nature paper, which showed that English over the last 100 years has outcompeted, you know, many regional languages like Welsh and Scottish Gaelic and things. And so if you look at the top panel there, like 100 years ago in Scotland or Wales, everyone spoke, say, Scottish Gaelic or Welsh. No one spoke English. Maybe a very small population, and now, right, essentially everyone speaks English, and no one really speaks the native language. And this is happening in many places. But there's also bilinguals. There's people who speak 2 languages, and there's people who speak 3 languages in many countries, Asian countries, European countries, right? Multilingualism. Bilingualism, of course, is more common, but actually there's, multilingualism as well. Uh, what I'll talk about is in the Indian context, but even in, say, many African countries, for example, it's very common to speak 3 languages or more. Uh, Now, multilingualism is known to delay the onset of Alzheimer's. So it is known that people who are bilinguals and trilinguals, the progression of Alzheimer's is little slower in them. This is known. And what we want to do is to actually couple with bona fide ODE, where these ODEs are developed from data on bilinguals and trilinguals. So the neurodegeneration and cognitive decline ODEs that you see are fairly generic. We want to get decay rates, comparing decay rates to normal patients, or say monolingual patients versus bi and trilingual. So in the Indian context where these guys are working, they have, several data sets where there are, bilingual and trilingual patients. Say in, West Bengal in India, people will speak 3 languages: English, Hindi, and Bengali, for example. And then look at the simulations. Okay. So from an analysis point of view, the coupling with just pure ODEs is little bit difficult, particularly if it's non-autonomous. If the ODEs are non-autonomous, here everything's autonomous, the way I set it up. But in the non-autonomous case, right, it's right, the compactness is more difficult. You can look, there's work, of course. Zelig is a big expert on this stuff. You can look at, other recent works. Uh, and the goal is then to compare decay rates and neurodegeneration, what comes out of the big simulations of monolinguals versus bilinguals. So this is on the cards, to be thought of, and also thinking of currently. Uh, there are other things that I'm interested in, to look at. One is other kinds of non-smooth reactions, both in the reaction term and also in the diffusion term, right? So the sort of P-Laplacian type of terms. And in all these things, you have something called finite time extinction, which complicates matters. So there's some progress with non-smooth reaction terms. You can look at, Aniket Banerjee's recent work. With the P Laplacian, I have been looking at that quite hard last, 3 months, 2, 3 months or so. I have a few things with uh, P between three halves and two. Below three halves, I don't have anything yet, but nothing to report. So that's also on the cards. Of course, this stuff has been being looked at from the language dynamics point of view as well. You can look at De Silva and collaborators' work, her students and collaborators, recent interesting paper. To the best of my knowledge, this is the first one applying FDE kind of techniques to language dynamics. And I think that's another hot research direction under this broad umbrella. Those are some of our current and future directions. So I'll stop here. Thanks for